The cosmos operates with a breathtaking precision, as if following a hidden instruction manual. We are going to investigate whether a single all-powerful superforce is the ultimate programmer of reality. By the end of this journey, you will see the universe in a completely new way, questioning the very nature of existence itself. We will uncover why gravity refuses to follow the same rules as every other force, and ask if our own consciousness might be part of the cosmic code. Does the universe feel more like a perfectly designed machine or a beautiful accident to you? This breathtaking cosmic precision hints at a deeper, hidden order. For centuries, physicists have pursued a grand dream, a single theory to explain everything. At the heart of this quest are the four fundamental forces that orchestrate every interaction in our universe. You are familiar with gravity, the force that keeps your feet on the ground and planets in their orbits. Then there is electromagnetism, the power behind light, electricity, and the very chemistry that makes life possible. But two other forces operate in a hidden realm, the atomic nucleus. The strong nuclear force is the incredibly powerful glue that holds the very protons and neutrons together, while the weak nuclear force drives the radioactive decay that heats the Earth's core and powers the Sun. For a long time, these four forces seemed completely separate, each with its own rulebook, but the greatest minds in science suspected a deeper connection. They embarked on a monumental journey to unify them, to show they are all just different faces of one single, all-powerful superforce, and they have already succeeded in a stunning way. In a monumental breakthrough, physicists managed to show that electromagnetism and the weak nuclear force are actually two sides of the same coin, merging them into what we now call the electroweak force. This was not just a simple combination. It required proving that at the incredibly high energies of the early universe, these two seemingly distinct forces behaved as one. This incredible achievement is like discovering that fire and ice are, at their core, the same fundamental substance. It proves that unification is possible. The search for this single cosmic architect, this superforce, is not just philosophical wonder. It is the central, driving mission of modern physics. Gravity is the cosmic sculptor, carving the paths of planets and the dance of galaxies. Yet for all its grandeur, it stands as the ultimate rebel in physics. While the other three forces have begun to merge into a unified picture, gravity remains stubbornly apart. This is the story of the lone wolf of the cosmos. Our modern understanding of gravity comes from Albert Einstein's theory of general relativity. He proposed a revolutionary idea that gravity is not a force in the traditional sense, but rather a warp in the very fabric of space and time. Imagine space as a vast, taut rubber sheet. A massive object like the Sun creates a deep dip in that sheet. The Earth, then, is not being pulled by an invisible string, but is simply rolling along the curved groove created by the Sun's presence. This elegant idea perfectly explains the motion of planets, the bending of light around stars, and even the existence of black holes. But here is the problem. The other three forces, electromagnetism and the nuclear forces, are described by an entirely different set of rules, the quantum world. In this realm, forces are transmitted by tiny packets of energy called particles. The electromagnetic force, for instance, uses photons. The quantum world is a realm of probability and uncertainty, where things can be in two places at once. General relativity, on the other hand, paints a smooth, continuous picture of space. When we try to apply the rules of quantum mechanics to gravity, the math completely breaks down. It produces nonsensical answers, infinities that cannot be reconciled. This creates a fundamental schism in our understanding of reality. We have two incredibly successful theories that each work perfectly in their own domain, but they speak completely different languages and refuse to talk to one another. This conflict is the single greatest unsolved problem in modern physics. unifying Einstein's graceful cosmic geometry with the chaotic, probabilistic quantum realm is the final frontier. Without this unification, we cannot understand the universe's very first moment, the singularity of the Big Bang, where all of reality was compressed into a tiny, infinitely dense point governed by both gravity and quantum effects. So the question remains, is gravity truly a fundamental outsider, or is its solitary nature merely a clue, waiting for the right key to unlock its secrets and reveal its place in a single, all-powerful superforce? The dream of a single cosmic architect did not end with the unification of electromagnetism and the weak force. The next logical step in this cosmic quest is even more profound, a theoretical framework known as the Grand Unified Theory. Its ambition is staggering: to merge the electromagnetic and weak forces with the powerful, strong nuclear force. This would weave three of the universe's four fundamental forces into one magnificent tapestry. Imagine if the forces responsible for sunlight, for the stability of every atom in your body, and for the nuclear furnace of the stars were all revealed to be different manifestations of a single underlying principle. That is the promise of a grand unified theory. These theories make a startling prediction that the proton, one of the fundamental building blocks of all matter, is not truly immortal. According to grand unification, protons should eventually decay, vanishing into a burst of energy after an almost unimaginable timescale. To us, a proton's lifetime seems eternal, but on the cosmic clock, it may just be ticking very, very slowly. The reason we have never observed this decay is tied to the immense energy required to see this unity in action. The forces only reveal their single nature under conditions of unbelievable heat and density, a state the universe has not experienced since the first fleeting moments after the Big Bang. Our most powerful particle colliders on Earth can only recreate a tiny fraction of that primordial energy, so we are left searching for indirect clues like the slow decay of a proton, for echoes of that perfect unity from the dawn of time. This profound schism between gravity and the quantum world is where string theory makes its grand entrance. It is arguably the most ambitious and mind-bending candidate for a true theory of everything. String theory proposes a radical shift in our understanding of reality's most basic building blocks. For decades, we have imagined the universe as being made of point-like particles, tiny dots with no internal structure. Electrons and quarks were thought to be these fundamental specks. String theory shatters this picture entirely. It suggests that at the heart of every particle, at the smallest possible scale, there is not a point but a tiny, vibrating loop of energy, a string. These strings are unimaginably small, so small that if an atom were the size of our entire solar system, a single string would only be the size of a tree on Earth. The magic lies in their vibration. Just like a single violin string can produce different notes depending on how it vibrates, these fundamental cosmic strings vibrate in distinct patterns. One specific vibration pattern might correspond to an electron. A different resonance creates a quark, and crucially, another unique vibration produces the particle that carries the force of gravity, the graviton. In this elegant symphony, every particle and every force in the universe, including the stubborn outsider gravity, emerges from the music of these strings. This is the theory's breathtaking promise, a single framework that could finally describe all of reality. It suggests that the four fundamental forces are not truly separate at all. They are simply different melodies being played on the same cosmic instruments. The conflict between the smooth geometry of space-time and the chaotic quantum world might simply vanish because both are born from the same underlying vibrational reality. The universe, according to this idea, is not a collection of things but a grand, harmonious composition. String theory's elegant solution comes with a truly cosmic price tag. It demands that our universe is not made of the three spatial dimensions we know, but of many more. According to the math, reality might require 10 or even 26 dimensions to make the vibrational symphony of strings work. This sounds like pure science fiction, but the idea is grounded in a serious attempt to solve the puzzle of gravity. So where are these extra dimensions? Why don't we see them? The leading theory is that they are compactified or curled up into a space so incredibly tiny that they are completely hidden from our view. Imagine a single, long garden hose stretching off into the distance. From far away, it looks like a simple one-dimensional line, but an ant crawling on that hose would experience a completely different reality. It could walk along the length of the hose, but it could also crawl in a tight circle around its thin circumference. The ant lives in two dimensions, one large and one very, very small. Our universe might be exactly like that. We move freely through the three large, familiar dimensions of length, width, and height. But other dimensions could be curled up into a complex, microscopic shape at every single point in space, a shape far too small for any instrument to detect. This compactification could be the key that finally unlocks the unity of all forces. The reason gravity appears so weak compared to the other forces might be because it is leaking or spreading out into these extra-dimensional realms, its strength diluted across realities we cannot access. In this breathtaking vision, the very fabric of our cosmos is infinitely richer and more complex than it appears, a multidimensional tapestry woven from hidden threads. Yet this beautiful concept of vibrating strings leads us to another profound and elegant idea, a kind of cosmic mirror known as supersymmetry. Supersymmetry proposes that for every particle we know, there exists a hidden supermassive twin. Every electron would have a partner called a selectron. Every quark would be matched with a squark. Even the force-carrying particles, like the photon, would have their own massive counterparts, such as the photino. This creates a perfect shadow universe of superpartners for every single particle in our own. Why would the universe require such an extravagant duplication? The answer lies in creating a more balanced and unified particle zoo. One of the biggest puzzles in physics is the hierarchy problem, the question of why gravity is so unimaginably weaker than the other forces. The math of our current model suggests that the quantum frenzy of known particles should make the Higgs boson, the particle that gives others mass, incredibly heavy, which would in turn make gravity appear far stronger than it actually is. This makes no sense with what we observe. Supersymmetry offers a beautiful fix. For every known particle contributing to this quantum frenzy, its superpartner would contribute with an opposite effect, perfectly cancelling out the problematic calculations and leaving the Higgs boson with the light mass we detect. This restores a natural balance to the cosmos. Furthermore, this theory provides a compelling candidate for the mysterious substance that makes up most of the matter in the universe, dark matter. The lightest of these superpartners, likely the photino or something similar, would be stable, invisible, and would not interact with light, exactly matching the description of dark matter that holds galaxies together. While we have not yet detected a single superpartner, supersymmetry remains a cornerstone of many theories of everything. It is the crucial ingredient that could harmonize the particle world, solve deep cosmic puzzles, and bring us one step closer to revealing a single, all-powerful superforce operating behind the curtain of reality. But this search for a single force leads us to an even deeper mystery. Look at the universe itself. Its very existence seems to hinge on a set of numbers so precise, so perfectly balanced that any slight change would make everything we know impossible. These are the fundamental constants. Think of them as the cosmic dials and knobs that were set at the moment of creation. The strength of gravity is one such dial. If it were just a tiny bit stronger, the universe would have collapsed back on itself in a catastrophic big crunch moments after it began. If it were slightly weaker, stars and galaxies would never have formed at all, leaving behind only a cold, thin mist of hydrogen. The mass of the electron is another perfectly set value. If it were different by even a minuscule fraction, the chemistry that builds atoms and molecules, the very chemistry of life, would simply fall apart. Stars would not burn, water would not flow, and carbon, the essential element for life as we know it, would never be forged in stellar furnaces. It is as if someone or something set these values with incredible care. The odds of all these constants randomly falling into the exact narrow range required for a life-supporting universe are astronomically small, like winning the lottery 1 billion times in a row. This incredible precision forces us to confront a profound question. Is our universe a staggeringly unlikely fluke, a single winning ticket in a cosmic lottery of dead, sterile universes? Or are these numbers evidence of something deeper, a preset architecture, a signature of that all-powerful superforce that wrote the rules specifically to allow for stars, planets, and conscious beings to eventually emerge? The constants of nature feel less like random numbers and more like lines of a cosmic code, carefully programmed to make our reality possible. This perfect fine-tuning of the cosmos leads us directly to a profound and deeply debated idea, the anthropic principle. At its simplest, the weak anthropic principle states a seemingly obvious fact that we can only observe a universe capable of producing us. It is a statement about our place in the cosmos. Any universe that did not have the right constants, the right conditions for life, would, by definition, have no one around to wonder about it. We exist, therefore we find ourselves in a universe that permits our existence. This feels almost like a tautology, a self-evident truth. But then there is the strong anthropic principle, a much more controversial and startling proposition. It suggests that the universe must, in some fundamental way, be constrained to have parameters that allow for the emergence of conscious life. This is not just an observation about our luck, but a statement about the laws of physics themselves. It implies that the universe is somehow compelled to be bio-friendly. Is this a profound clue pointing toward a deeper design, perhaps the signature of that all-powerful superforce that intentionally calibrated the cosmic dials from the very beginning? Or is it merely a clever way of sidestepping the real question, a philosophical trick that explains nothing? The debate rages. One side sees the strong anthropic principle as a gateway to a truly cosmic purpose, a universe that is not just habitable but was meant to be so. The other side sees it as an empty statement, no more profound than noting that fish live in water. They argue it is not an explanation at all, but a refusal to search for a deeper physical reason why these constants have the values they do. This forces us to confront the very nature of our inquiry. Are we simply the beneficiaries of an astronomically lucky roll of the dice in a vast, perhaps infinite multiverse of dead worlds? Or are the laws of nature themselves pointing toward our existence as an inevitable outcome of a single, unifying cosmic principle? The answer to this question may determine whether we live in a universe of chance or one of profound, underlying intention. The intense debate over cosmic fine-tuning pushes our gaze back to the very origin of everything. There is one moment in history where the dream of a single superforce was not a theory but a reality. We must journey to the instant of the Big Bang itself. In the first fleeting fraction of a second, the entire cosmos was an unimaginably hot, dense singularity. Within that blazing forge, the conditions were so extreme that the four fundamental forces as we know them did not exist. They were fused together, perfectly unified into one primordial, all-powerful superforce. In that singular state, there was no distinction between gravity and electromagnetism, no separate nuclear forces. There was only one law, one rule governing a perfectly symmetrical reality, but this perfect unity could not last. The universe was expanding and cooling at a ferocious rate. As it did, this single superforce began to undergo a series of cosmic phase transitions. Think of it like water. When water is in its liquid state, it is uniform and symmetrical. But as it cools and freezes into ice, that symmetry is broken. The water molecules lock into a specific crystal structure, choosing one particular pattern out of many possibilities. In much the same way as the infant universe cooled, the primordial superforce froze. Its perfect symmetry shattered. With each drop in temperature, a piece of the superforce broke away and crystallized into the distinct forces we recognize today. First, gravity is thought to have separated, setting itself apart as the architect of space and time. Then, the strong nuclear force split off, becoming the glue that would bind atomic nuclei. Finally, in a last parting, the electroweak force separated into the electromagnetic and weak forces we observe now. This cosmic freezing left us with the four seemingly separate interactions that construct our reality. The universe we inhabit is the cold, crystallized remnant of that initial perfect unity. Every particle interaction, every orbit of a planet, is a consequence of that primordial breaking of symmetry. This raises a staggering possibility. The search for a theory of everything is not the quest to invent a new idea. It is the attempt to reverse engineer the original state of the cosmos, to rediscover the single superforce that was the universe's first and only law. Are the forces we see today merely frozen fragments of that ultimate unity, waiting for us to melt them back together with the heat of our understanding? This bizarre concept of a frozen superforce finds a strange echo in the quantum realm, a domain where our everyday logic completely falls apart. Here, particles exist in multiple places at once, and reality itself seems to be a game of probability. But the most profound challenge to our classical view comes from a phenomenon so strange that even Albert Einstein rejected it, calling it spooky action at a distance. We now know it as quantum entanglement. Imagine you create a pair of electrons in such a way that their properties are linked, like two coins spinning in perfect sync. Now you take one of these electrons and instantly transport it to the farthest star in another galaxy. You then measure the spin of the electron you kept. The moment you do this, its distant twin, billions of light years away, instantly snaps into the opposite spin. This connection is instantaneous, seemingly faster than the speed of light. It is as if the two particles are not separate entities at all, but two parts of a single, unified system, no matter how vast the distance between them. This is not science fiction. It has been confirmed repeatedly in rigorous experiments. This non-locality shatters our most basic assumptions about space and separation. In a universe governed by classical physics, information cannot travel faster than light. But entanglement suggests that at a fundamental level, the universe is not made of isolated things. It behaves as a deeply interconnected whole. Could this spooky action be a glimpse into the underlying architecture of reality, a hint that the separations we perceive are an illusion? Perhaps the cosmos is not a collection of distinct points in space, but a single, unified field where everything is intimately linked. This quantum weirdness does not just challenge our ideas about space, it questions causality itself. If the state of one particle instantly determines the state of another, what does cause and effect even mean on this fundamental level? The entangled particles seem to be operating from a shared instruction manual written at the moment of their creation, a set of rules that transcends the space between them. This profound interconnectedness feels like a ghostly remnant of that primordial superforce, a lingering whisper of the universe's original, perfect unity before the great freezing and separation of the forces occurred. Is the quantum realm showing us that the cosmos, for all its apparent fragmentation, is still fundamentally one? This quantum interconnectedness forces us to question the very nature of reality itself. Could the three-dimensional world we experience be a magnificent illusion? This is the startling proposal of the holographic principle, an idea born from the deepest puzzles of black hole physics. It suggests that all the information needed to describe everything within a volume of space, every star, every person, every atom, might not be contained within that volume at all. Instead, it could be perfectly encoded on a two-dimensional surface that surrounds it like a cosmic movie screen. Think of a hologram on your credit card. That shimmering, three-dimensional image is not truly deep. It is projected from a flat, two-dimensional film etched with microscopic patterns. In the same way, our universe, with its vast, immersive depth, might be a grand projection from a simpler, flatter reality at the boundary of the cosmos. The implications of this are staggering. It would mean that the true, fundamental description of reality requires one less dimension than we perceive. The messy, complex interactions of particles and forces in our three-dimensional world could be simplified into a more elegant, two-dimensional code written on the surface of the universe. This directly confronts the challenge of unifying gravity with quantum mechanics. In this holographic view, gravity in our three-dimensional world might emerge from the quantum laws operating on that distant two-dimensional surface. It is as if the stubborn rebel force is not fundamental at all, but a consequence of a deeper, simpler physics playing out elsewhere. Could the search for a single superforce be vastly simplified if we realized we are not looking at the source code, but only at the projection? The holographic principle suggests that the ultimate cosmic architect might not be working in three dimensions, but on a two-dimensional canvas, painting a universe of such rich detail that it fools even us into believing we are solid beings in a deep, expansive world. Are we, and everything we know, just ghostly data flickering on the surface of a reality we cannot yet see? This quantum strangeness inevitably pulls us toward the most mysterious frontier of all, the nature of consciousness itself. If reality at its most fundamental level is a cloud of probabilities, what exactly triggers it to snap into the solid, definite world we experience? One of the leading interpretations of quantum mechanics, the Copenhagen interpretation, provides a startling answer. It proposes that a particle does not have a definite position or state until it is measured. Before observation, it exists as a blur of possibilities, a probability wave. The very act of observing it, of measuring it, forces this wave to collapse into a single, concrete reality. This raises a profound and deeply unsettling question. What qualifies as an observer? Is it a sophisticated machine, a camera, a computer, or does it require something more, something with awareness? Could consciousness itself be the active ingredient that crystallizes possibility into actuality? This idea pushes us into speculative but breathtaking territory. It suggests that mind and cosmos are not separate. Consciousness may not be a passive spectator that emerged late in cosmic history. It might be a fundamental participant woven into the very fabric of physical law. Is it possible that the universe required a conscious observer to bring it into full being, that the superforce we seek is not just a blind, mechanical principle, but one that incorporates perception as a core feature? This would mean that you, me, every conscious being is not just living in the universe, but is an essential part of its ongoing creation. We are not just reading the cosmic code, we are executing it with every glance, every measurement, every thought. Could the ultimate unifying force be a synthesis of physical law and conscious awareness, a universe that becomes real by being perceived? Could this bizarre link between consciousness and reality be more than a quantum quirk? What if mind is not a rare accident in a dead cosmos, but a fundamental property of existence itself? This is the radical proposition of panpsychism, a philosophy that turns our entire world view upside down. Panpsychism suggests that consciousness did not mysteriously emerge from complex arrangements of unconscious matter, like a ghost from a machine. Instead, it posits that some form of mind or proto-consciousness is a basic and universal feature of the universe, as fundamental as mass or charge. In this view, the building blocks of reality are not just tiny, mindless billiard balls. An electron, a quark, or even a photon might possess an infinitesimal spark of subjective experience. Not thought, not reason, not self-awareness as we know it, but a raw, primitive form of feeling. This is not to say an atom is contemplative or a rock is sad. Their inner life would be unimaginably simple, a faint hum of existence against the cosmic backdrop, but it would be there. This idea completely reframes our search for a superforce. It suggests the ultimate architect of reality might not be a cold mathematical equation, but a principle that inherently integrates mind and matter from the very beginning. The single unifying rule would not be a blind mechanical push and pull. It could be a law of experiential reality where the physical and the mental are two sides of the same coin. How could this possibly work? Consider the integrated information theory, a modern scientific framework that aligns with panpsychist thought. It proposes that consciousness corresponds to a system's ability to integrate information. The human brain, with its trillions of interconnected neurons, generates a rich and deep conscious experience. A thermostat with its simple on-off switch might have only a minuscule flicker. And an electron with its most basic properties might possess the faintest whisper of all. In this grand spectrum, everything has an inner dimension. The universe is not just made of stuff, it is made of experiencing stuff. This solves the so-called hard problem of consciousness, the mystery of how subjective experience arises from objective matter, by declaring it a false problem. Experience was always there, a fundamental ingredient. The superforce, then, would be the law governing how these countless tiny sparks of experience combine and organize to create more complex minds like our own. The cosmos is not a giant machine. It is a vast awakening mind, and we are a part of its growing self-awareness. Is the universe itself conscious, and are we its way of knowing itself? This ancient dialogue between science and faith finds a modern battleground in the search for a superforce. For centuries, when natural phenomena like lightning or disease had no scientific explanation, they were often attributed directly to the will of a deity. This line of reasoning has a name, the God of the Gaps argument. It places divine action in the ever-shrinking gaps of our scientific understanding. As physics advances, meticulously mapping the laws that govern the cosmos, these gaps grow smaller. The quest for a single, all-powerful superforce represents the ultimate ambition of this scientific endeavor, an equation that would leave no room for such gaps. This raises a profound and deeply personal question. If science one day achieves its grand dream and discovers a theory of everything, a single mathematical rule from which all of reality unfolds, would that eliminate the need for a creator? Or would it, instead, simply describe the breathtaking mechanism through which such a creator operates? One perspective sees a final theory as the ultimate closure, a demonstration that the universe can run perfectly well without any external pilot, a self-contained system of cause and effect. Yet another, equally valid view might see that same equation not as a refutation of divinity, but as its ultimate revelation. Finding the fundamental code of the cosmos could be interpreted as uncovering the master blueprint, the elegant language in which the laws of the universe were written. Is the superforce the answer that makes God obsolete, or is it the very signature we have been searching for all along? The beauty of this mystery is that the answer may not lie in the physics itself, but in the meaning we choose to find within its breathtaking unity. This line of thought brings us to a modern and provocative possibility, the simulation hypothesis. What if our entire universe, with all its galaxies, forces, and conscious beings, is not fundamental reality, but an incredibly advanced digital construct? The idea is simple yet staggering. A civilization far more technologically mature than our own could be running our cosmos as a simulation on a computer of unimaginable power. In this scenario, the laws of physics are not fundamental truths. They are simply the programmed rules of the software. The four fundamental forces, gravity, electromagnetism, and the nuclear forces, are just the algorithms that govern how the simulation renders interactions. The puzzling constants of nature, those perfectly tuned numbers, are not evidence of a cosmic designer, but the input parameters set by the programmers. Even the bizarre quantum effects like entanglement and wave function collapse could be explained as efficient computational shortcuts. When two particles are entangled, they don't need to communicate faster than light. They are simply two objects sharing a single line of code, a single variable that is updated instantly. The probabilistic nature of quantum mechanics could be the simulation's way of saving processing power, only calculating the precise properties of a particle when an observer, a user of the simulation, looks at it. This would elegantly solve the measurement problem, making consciousness not a fundamental creator of reality, but a user interface that forces the program to render details on demand. The arguments for this are not purely philosophical. Some physicists point to the finite, pixelated nature of reality hinted at by quantum mechanics and the holographic principle. If information in a volume of space is finite, stored on a two-dimensional boundary, it behaves exactly like a cosmic hard drive. Our universe appears to have a maximum resolution, a Planck length, below which the concept of distance loses meaning. This is precisely what you would expect from a simulated reality, a built-in limit to prevent infinite calculations from crashing the system. Yet powerful counterarguments exist. Is such a simulation even possible without requiring infinite computational resources? Simulating every quantum event in every atom of every star in trillions of galaxies seems like an unfathomable task. Perhaps the simulation is not so detailed, rendering the microscopic world only when necessary, like a video game that only draws the trees you are looking at. But if our reality is a simulation, then the programmers themselves must exist in a base reality, a parent universe with its own, presumably different laws of physics. This leads to an infinite regress, a chain of simulations within simulations. If simulating universes is possible, then statistically, there are likely billions of simulated realities for every one base reality, making it overwhelmingly probable that we are in one of the simulations. The most profound implication for our search is this: if the simulation hypothesis is true, then the single, all-powerful superforce we have been seeking is not a law of a fundamental cosmos. It is the master algorithm, the ultimate source code written by the architects of our digital prison or playground. Our entire quest for a theory of everything would be the process of reverse engineering our own programmed reality, discovering the rules that our creators wrote into existence. Are we uncovering the deepest secrets of the cosmos, or are we merely reading the user manual for our own cage? Einstein's own theories of relativity hint at a cosmos where time itself is an illusion. They suggest a model known as the block universe, where past, present, and future do not flow but simply are. Imagine reality not as a movie playing frame by frame, but as an entire film reel already complete. In this four-dimensional block, every event that has ever happened or ever will happen exists simultaneously, fixed in its place within the fabric of space-time. Your birth, the formation of the sun, and the death of the last star are all equally real and present, just at different coordinates in the cosmic map. This is not science fiction, it is a direct interpretation of the equations that govern our universe. If this is true, then the passage of time is a profound trick of perception, a shadow cast by our conscious minds as we move along our own world lines within the block. We feel ourselves rushing from the past toward the future, but according to this view, the future is already out there, waiting. This leads us directly to the ancient philosophical specter of determinism. If the entire block is static and unchanging, then every choice you believe you are making was written into the cosmic structure from the very beginning. The words you are hearing right now and your reaction to them were determined by the initial conditions of the Big Bang, locked into place as the superforce fractured and the universe cooled. Is free will nothing more than a compelling story we tell ourselves, a necessary illusion for conscious beings navigating a predetermined track? This places the idea of a superforce in a startling new light. That single, unifying principle would not just be the source of the laws of physics, it would be the author of a fixed, unalterable story. The superforce would have set the initial dials, and the entire, vast block of reality would have unfolded from that moment with no deviation possible. Yet, this rigid picture clashes violently with the quantum world we explored earlier. In the quantum realm, probability reigns and particles exist in a haze of maybes until observed. How can a universe of definite, pre-written events be reconciled with a universe built on fundamental uncertainty? Perhaps the block is not as solid as it seems. Maybe the future is not a single, etched path, but a branching tree of possibilities, with every potential outcome existing in a state of quantum superposition until consciousness collapses one into reality. Or maybe our understanding of time itself is still hopelessly primitive. The search for the superforce is not just a search for unity among forces, it is a search for the true nature of time, and with it, the ultimate meaning of our own choices. The rigid determinism of a block universe feels utterly alien to the cosmos we actually observe. Out there, in the vast galactic deep, we find evidence of a reality governed by forces we cannot see, pushing and pulling the very fabric of existence in ways that defy our current laws. The universe is not running on a predetermined track. It is being shaped by two profound and invisible hands, dark matter and dark energy. Together, these two mysteries constitute 95% of everything that exists. All the stars, planets, and galaxies we can see, every single atom you are made of, accounts for a mere 5% of the cosmos. The rest is a complete enigma. Dark matter was first suspected when astronomers noticed that galaxies were spinning far too fast. The visible matter in them, the stars and gas, simply did not provide enough gravitational glue to hold them together. They should have flown apart long ago. Something invisible, something that does not interact with light at all, must be providing the extra gravity, weaving an unseen scaffold that holds the galaxies intact. Think of it like this: you see a distant, swirling pinwheel in a strong wind. Based on the visible paper and its delicate structure, it should tear itself to pieces. But it doesn't. This tells you there must be an invisible framework inside, a rigid wire holding it all together against the forces trying to rip it apart. Dark matter is that cosmic wire. Then there is its even stranger counterpart, dark energy. In the late 1990s, scientists made a shocking discovery. They found that the expansion of the universe is not slowing down due to gravity, as everyone expected. It is speeding up. Something is actively pushing space itself apart, a repulsive force that grows stronger as the universe gets emptier. We call this something dark energy. It behaves like a kind of anti-gravity woven into the vacuum of space itself. So we have a cosmic tug-of-war on the grandest scale imaginable. Dark matter, with its gravitational pull, works to build structure, pulling galaxies and clusters together. Dark energy works to tear it all apart, accelerating the expansion of space and driving the cosmos toward an eventual cold, dark, and lonely end. We have given them names, but we have no idea what they truly are. They are not made of atoms or any known particles. They do not emit or absorb light. They simply and overwhelmingly are. This forces a humbling question upon our quest for a superforce. Our current theories, from general relativity to the standard model of particle physics, were built to explain the visible 5%. They are completely silent on the nature of the 95% that actually governs the cosmos's fate. Could it be that our failure to find a single, unifying principle is because we have been studying only a tiny fraction of the puzzle? Perhaps dark matter and dark energy are not separate mysteries at all, but two different faces of the same underlying phenomenon, a single dark sector that is the true manifestation of the superforce. Unlocking their secrets may not be a side quest in physics. It might be the final, crucial step to hearing the universe's fundamental note, a note played not in the light, but in the profound and shaping darkness. This radical simplification of reality leads us to an even more profound possibility. What if the universe is not just running on math, but actually is math? This is the core of the mathematical universe hypothesis, an idea that pushes the quest for a superforce into truly abstract territory. Proponents like Max Tegmark propose that our physical reality is not merely described by mathematics, which is the successful method of all science. Instead, they argue that the universe is a mathematical structure itself. Think of a perfect, immaterial triangle. It has defined properties, angles that add up to 180 degrees, a specific area. It exists as a pure, abstract relational object, independent of anyone drawing it. Now, scale that idea up to an unimaginable degree. The mathematical universe hypothesis suggests that our cosmos, with all its particles, forces, and dimensions, is just as real and just as mathematical as that triangle. We are not participants in a physical universe that obeys mathematical rules. We are patterns within a vast, free-standing mathematical object. In this view, what we call the laws of physics are not directives programmed into reality. They are simply the inherent properties and relations of this grand mathematical structure. The force of gravity is not a force in the traditional sense, but a geometric property of the structure, much like the angles of a triangle. An electron is not a tiny ball, but a specific excitation in a cosmic equation. This reframes our entire search for a superforce. That single, all-powerful unifying principle would not be a physical mechanism or a vibrating string. It would be the core, foundational mathematical relation from which the entire structure logically and necessarily flows. Finding a theory of everything would not be discovering what the universe is made of, but which mathematical structure it is. This idea dissolves the age-old question of why mathematics is so unreasonably effective at describing the world. The answer becomes simple because the world is mathematics. The constants of nature are no longer mysterious dials that needed tuning. They are fixed, immutable parameters of the specific mathematical object we happen to inhabit. The cosmic code is not written in the language of physics, it is written in the language of mathematics, and we are living inside one of its proofs. This leads to a staggering implication, the existence of a multiverse not of parallel worlds, but of all possible mathematical structures. Every self-consistent mathematical system exists in just the same way our universe does. Most would be barren, lifeless abstractions, but a tiny fraction would have the complexity to contain self-aware substructures that perceive themselves as living in a physical world. We find ourselves in one that allows for our existence. This makes the anthropic principle a logical necessity within a vast mathematical landscape. So, is the ultimate superforce simply the cold, beautiful, and unchangeable truth of mathematics itself? Are we, in our quest to understand the cosmos, merely a part of the universe becoming consciously aware of its own fundamental mathematical nature? But these breathtaking ideas face a wall of profound challenges. The quest for a single superforce is not a smooth path to enlightenment. It is a journey fraught with roadblocks, both experimental and philosophical. Consider the grand hopes we placed in our most powerful scientific instrument, the Large Hadron Collider. This monumental machine was built to probe the frontiers of physics, and its discovery of the Higgs boson was a triumph. Yet, for the theories that promise unification, its results have been deeply sobering. The collider has found no evidence for the extra dimensions predicted by string theory. It has detected no signs of the superparticles required by supersymmetry. These were not minor predictions, they were central pillars of our most promising frameworks for a theory of everything. Their absence forces a difficult question. Are we on the wrong track, or are the energies required to see this unity simply beyond our technological grasp? The energies at which these forces truly merge are stupendous, a quadrillion times more powerful than what the Large Hadron Collider can produce. We are trying to hear the universe's fundamental note by listening for a faint echo from the first moment of creation, an echo that grows fainter with every passing second. This leads to a more fundamental crisis, the problem of testability. If a theory makes predictions that cannot, even in principle, be verified by experiment or observation, does it still belong to the realm of science? Or has it crossed into a new kind of metaphysics, a beautiful and compelling philosophy that is, ultimately, untestable? This is the razor's edge that modern physics walks. We are developing mathematics of unimaginable beauty to describe realities we may never be able to access. This struggle sparks a fierce debate about the very nature of scientific progress. Is the universe ultimately knowable? Is there a final, elegant equation waiting for us at the end of the road, a theory of everything that would answer all physical questions? Or is science an endless frontier where every answer simply reveals a deeper, more complex layer of questions? Perhaps the search itself is the point, a never-ending conversation with the cosmos. Finding a final theory might not be a victory, but an ending, closing the book on the greatest mystery of all. The silence from our greatest experiments may be a message, not that we have failed, but that the universe is far stranger and far more wondrous than any single theory could ever contain. This profound silence from our experiments forces us to consider a truly cosmic escape clause. The multiverse hypothesis offers a radical answer to the puzzle of fine-tuning. If our universe is just one bubble in an infinite, bubbling foam of realities, then the perfect constants we observe require no special explanation. They are simply the local bylaws of our particular cosmic neighborhood. Theories like eternal inflation paint a picture of a primordial meta-universe, forever expanding and sporadically spawning new baby universes in a process without end. Each of these bubbles could crystallize with a random set of physical laws and fundamental constants. In most of these universes, the numbers would be wrong. Gravity might be too weak for atoms to form, or the strong force too strong for stars to ignite. These would be dead, sterile realities, but in a cosmos of infinite possibilities, a universe with just the right numbers for life becomes a statistical certainty. We, of course, find ourselves in one of those rare, habitable bubbles, not because it was designed, but because we could not exist anywhere else. String theory adds its own compelling layer to this idea with the concept of the landscape. The math suggests there are not just a handful, but an astronomically vast number of possible stable configurations for the extra dimensions, perhaps 10 to the 500 different versions. Each configuration corresponds to a universe with a different set of particles and forces, a different value for the strength of gravity or the mass of the electron. Our entire cosmos, then, is just one tiny point in this gargantuan landscape of possibilities, one specific way the strings decided to vibrate and curl. This framework seems to dissolve the need for a single superforce or a cosmic designer. There is no one set of laws to unify because every possible set of laws exists somewhere. The quest for a unique theory of everything might be fundamentally misguided, replaced by a cosmic catalogue of every possible physical reality. But does this truly solve the mystery, or does it merely push it back one step? Who or what wrote the rules for the meta-universe, the overarching engine of eternal inflation that births all these different worlds? The multiverse might not be an answer, but the start of an even deeper, more bewildering question. Our own minds may be the final, unsolvable puzzle in this cosmic search. The human brain is a magnificent instrument evolved to spot predators, find food, and navigate social hierarchies. It was not designed to intuit the true nature of 11-dimensional strings or a reality that exists as a static mathematical block. We are trying to perceive the fundamental architecture of the cosmos using a tool that was optimized for survival on the African savanna. This creates a profound and likely unbridgeable gap. Think of a goldfish in its bowl. It might have a complex understanding of its world, the way the light shifts at a certain hour, the pattern of the pebbles at the bottom, the giant blurry shapes that appear outside the glass. But could it ever truly comprehend the concept of water? Could it understand that it is immersed in a substance with specific chemical properties, a substance that is delivered through a vast city-wide plumbing system? The water is its entire reality, yet its true nature remains forever beyond the fish's grasp. We are in a similar position. We are swimming in space and time, bound by its laws. Our consciousness, our very logic, is a product of this specific cosmic environment. Asking our brains to understand what lies outside of or before this framework might be like asking a caveman to reverse engineer a smartphone. He could perhaps appreciate its smooth, shiny surface, but the concepts of software, binary code, and global satellite networks would be utterly meaningless. Our scientific tools are extensions of our senses, and they too hit a hard wall. We can only probe reality down to a certain scale, the Planck length, and we can only see back to a certain moment, the Planck time, before our equations break down into nonsense. This is not necessarily a failure of our instruments, but a fundamental limit of measurement and meaning in our universe. The ultimate superforce, if it exists, might operate on a logical plane so alien to our own that its description would be as incomprehensible to us as a symphony is to a stone. This does not mean the quest is worthless. The struggle to understand, to push against the boundaries of the knowable, is what defines our species, but it does add a necessary layer of humility to our grandest ambitions. We may be destined to forever map the shoreline of a vast and unchartable ocean, never fully grasping the mysterious currents that lie at its depths. Perhaps our relentless scientific quest is itself an echo of a much older human intuition. For thousands of years, long before particle accelerators or quantum theory, the great wisdom traditions of the East were contemplating the same fundamental unity using a very different language. In Taoism, the ultimate reality is not a force but a way, the Tao. It is the unnameable, all-pervading source from which all things emerge and to which they all return. The Tao is not a god or a singular entity to be worshipped, but the natural order of the universe itself, a flowing, dynamic balance of opposites embodied in the familiar symbol of yin and yang. It is the single principle that unifies light and dark, action and stillness, creation and destruction. This is not so different from a physicist seeking a single mathematical principle that unifies all forces and particles. The Tao that can be spoken is not the eternal Tao, they say, a profound acknowledgement that the ultimate truth may transcend any description, including a final equation. Similarly, in Hinduism, the concept of Brahman represents the ultimate, unchanging reality, the infinite, impersonal ground of all being. The entire universe of separate objects and individual souls, what we call reality, is termed Maya, often translated as illusion. This does not mean the world is not real, but that its appearance of separateness is a kind of cosmic veil. Underneath the diverse phenomena, everything is a manifestation of the one unified Brahman. The goal of spiritual practice is to see through the illusion of separation and experience this fundamental oneness. Now, consider the quantum entanglement we discussed earlier, where two particles remain connected across vast distances as if they are one system. Is this modern physics simply providing evidence for what mystics have described for millennia, that separation is a superficial feature of a deeply interconnected whole? One of the most beautiful metaphors for this comes from Buddhism in the concept of Indra's net. Imagine a vast cosmic net stretching infinitely in all directions. At every intersection of this net hangs a brilliant, perfectly polished jewel, and in the surface of every single jewel, you can see the reflections of all the other jewels in the entire net. Each jewel contains the whole, and the whole is contained in each part. A change in one jewel, a single flaw or a new sparkle, is reflected in all the others. This is a stunningly precise poetic image for a holographic, entangled universe where every part encodes information about the whole. The search for a superforce in physics, a single rule from which all others derive, is a scientific parallel to this spiritual insight. It is the search for the one jewel whose structure explains the reflection in all the others, or perhaps the realization that there is only one jewel, seen from an infinite number of perspectives. The convergence is startling. The physicist seeks a unified field. The mystic speaks of experiencing a unified reality. One uses the language of mathematics and experiment, the other the language of meditation and direct perception. But both are pointing toward the same breathtaking possibility, that beneath the apparent chaos and diversity of the cosmos lies a profound, elegant, and singular unity. Could it be that our most advanced science and our most ancient wisdom are finally beginning to tell the same story? We are left with a constellation of possibilities, each vying to be the ultimate truth. So where does the evidence point? The purely mathematical universe offers a stark and beautiful elegance. If reality is just a freestanding mathematical structure, then the perfect order we observe is no surprise. It is simply the logical outcome of the equations we inhabit. There is no programmer, no designer, just the cold, necessary truth of numbers. This explains the unreasonable effectiveness of mathematics perfectly, but it leaves us as sentient patterns in a vast, indifferent proof. The simulation hypothesis, on the other hand, provides a startlingly practical answer to fine-tuning. The precise constants are just the initial settings chosen by advanced beings. The weird quantum effects are efficient computational tricks. It turns the cosmos into a product and our quest for understanding into a process of debugging the system. Yet it pushes the biggest question one level up: who created the programmers and what are the laws of their base reality? The conscious cosmos, or panpsychism, weaves mind directly into the fabric of existence. It solves the hard problem of consciousness by declaring it a fundamental feature, not an emergent illusion. This view feels deeply resonant, suggesting the universe is not a dead machine but an experiencing, awakening entity. But it struggles to provide testable predictions, resting more on philosophical elegance than empirical proof. Finally, the multiverse seems to be the ultimate escape from fine-tuning. With an infinite number of universes, one with the right conditions for life is inevitable. We just got lucky. This is a powerful argument, but it can feel like a philosophical surrender. It explains our existence by making it utterly mundane within an infinite sea of failure, and it raises the perplexing question of what mechanism generates this endless cosmic foam in the first place. Weighing these options, the most compelling picture may be a synthesis. Perhaps the mathematical universe and the multiverse are two sides of the same coin, where all possible mathematical structures exist and we perceive one. Maybe consciousness is the interface that allows this abstract math to become a lived experience. We lack a single, definitive answer, but the very act of searching reveals a profound pattern. Whether through physics or philosophy, science or spirituality, we are consistently drawn back to a single, inescapable conclusion. The cosmos, in all its splendid complexity, appears to be a unified whole. The separations between forces, between objects, and even between mind and matter may be the grandest illusion of all. The most plausible truth is not a specific theory, but the underlying principle of unity itself. We have journeyed from the four familiar forces of nature to the hidden vibrations of strings. We have scaled the towering idea of a multiverse and plunged into the depths of our own consciousness. We have encountered the silent, overwhelming presence of dark matter and dark energy, and questioned whether our reality is a grand simulation or a freestanding mathematical truth. Yet a single, definitive answer to the Superforce remains just beyond our grasp. Perhaps the most profound discovery in this entire quest is not a final equation, but a recurring pattern. Across every frontier of physics and philosophy, we are confronted by the same breathtaking theme, a universe that appears fragmented and chaotic on the surface, but points relentlessly toward an underlying, elegant unity. The search itself reveals a cosmos of immense beauty and deeper mystery, a puzzle that may be infinite in its complexity. So we leave you with this final, open-ended question, one that has echoed through the ages and now rests with you. What do you think? Is there a single, all-powerful superforce orchestrating the cosmic symphony? Or is the cosmos an endless, beautiful chaos waiting to be explored? Share your thoughts in the comments below, and if you enjoyed this journey to the edge of understanding, subscribe for more cosmic mystery.